Thanks to the organizers for the opportunity. So I'll start working. I'll start talking about MeerKLASS. So MeerKLASS, as Saurabh mentioned earlier, MeerKLASS is a unique survey where we use single dish and interferometric observations to do cosmology. Single dish part is primarily used for H1 intensity mapping, and we are trying to do a continuum survey with the interferometric part. So this escape precursor is planned for about 2,500 hours, and we plan to observe in the southern hemisphere, avoiding the galactic plane for about 10,000 square degrees over next 5 years. And now in the bottom panel, you can see the expected survey regions that we plan to observe. And here are some lists which part has been already observed and in which band. So the band information is given here, and this is the redshift that it will cover. But this particular region has been chosen because it has quite nice overlap with different optical and infrared surveys, which is shown here. And as DAISY and Euclid has already started giving us relevant data sets, we have considerable overlap with them, and the foremost will be having a quite a significant overlap. So our proposal has been now elevated to XLP. We have been awarded 1,000 hours for next 2 years. So intensity mapping team has been doing a great work, and they have detected H1 intensity maps in cross correlation with Wiggle-Z and gamma in L band from 2 different patches in the sky, which is really encouraging and shows that this particular technique works. Now detection in auto power spectrum is still ongoing. But however, today I'll discuss the commensal continuum survey. So to do this survey, before we move on to this continuum survey, it is very important that we understand how the observation is being done. So in this particular case, to avoid the change in the ground model, what we do, we fix the telescope in a particular elevation and then move it in azimuth like this, which is shown here, at a rate of approximately 5 into cos of elevation, so that it has a fixed rate in the sky. And this process creates this jagged pattern in the sky in array-deck coordinates. Okay, so this has an advantage that it can observe a very large region of the sky within very short time. And we observe this twice, once the field is rising, another when the field is setting. And these are the patterns that you get, and different kinds of sensitivity can be drawn. Okay, so this technique is called on the fly that we are going to use because telescope never stops. This is primarily very interesting because it's a commensal survey. So we are not asking for any other time from the telescope. It's the whatever H1 people ask, we use that. So we have already observed about 2,000 square degrees in UHF band and about 400 square degrees in L band. The survey is fast. We have multi-wavelength data in these regions. And the idea is that after this survey, we will have a sensitivity of about 25 microjansky in UHF band with a fairly decent resolution. Here is a comparison of the expected sensitivity with all other survey in the southern hemisphere. Okay, so this is the pipeline that we have developed. So we start with some observed measurement set and then do a bunch of things and reach multiple measurement sets of 2 seconds. Now, these steps some of them are pretty standard, some of them are non-standard. Some of the non-standard cases are this: we need to go and find out which antennas are able to follow the other antennas and which antennas are not. And depending upon that, we need to flag different bad and very bad antennas. Some of the standard things are like RFI flagging, and you can see from here UHF band is expected to perform better than L band. So after we get these measurement sets, we move on to the imaging part, which is shown here. And we do the imaging in DD facet, and we combine the visibilities during the imaging. Now, this comes with a challenge because of this particular technique. We have a difficulty in the software implementation, and currently the delay is set to a particular azimuth and elevation for the whole scan. So although your telescope is pointing in this region, your baselines are pointing always here throughout the observation. So that will create a smearing. And we have estimated the smearing. It is fairly controllable within 3–4%. Now the telescope is also moving within that 2 seconds of the time. So that will introduce a slightly oblate shape in the primary beam response. That will also create some small error in the fluxes that we extract from the image. But again, we have estimated that, and that is also within few percent. But the elephant in the room is that the delay is not even changing within that 2 seconds. So it never tracks the sky. So that introduces quite a significant amount of smearing. And as an example is that if you have a 2-second tracking observation, you expect your delay center or the pointing center to be centered around wherever you want your phase center to be. Whereas in our case, it moves. And that creates this smearing along one direction. We have a very nice estimate of like what is the smearing that we expect. However, the smearing is so severe that we cannot just do a scaling and correct for the smearing. However, we have developed a technique where we use internally in DD facet, we use this smearing calculation and apply them to the PSF of the image. And we scale the PSF accordingly and deconvolve the image with this modified PSF. So this gives us correct fluxes for the sources, and the source model is free of smearing. But we take a toll in the resolution, particularly along RA direction, because the sky moves in that direction. Okay, but the good news is from this year, this will be fixed. And we have a chat with the software team. They now understand what is the difficulty, and they have promised us they will fix it. Okay, so what kind of effect do we get once we do the smearing correction? So in the left-hand side, I'm showing an image without any correction. And in the right-hand side, if we apply the correction, so our models are compact, the errors are less, and the artifacts are mostly reduced. Okay, so after this whole imaging pipeline, mosaicing, we go and store the beam and smear corrected image cube to the disk. And these are our final data product. So these, in the left, I'm showing you the imaging parameters that we use. And in the right, I'm showing you the typical exposure time for one night of observation with rising and setting. And the bottom, the expected sensitivity in a very optimistic scenario. However, it is difficult to do imaging, including all the measurement sets in the field. So what we do, we divide the measurement sets into small chunks and create images with these small chunks. So this is one of the image that we have. This work is done by Sarvesh. And we can see that only with 4 nights of data, we can reach a flux scale of 50 microjansky. Just to be clear, that we have around 40 of these in this particular field. So we expect to go down much. So this is a comparison with the RACS and MeerKAT, and we can see that MeerKAT is able to capture one of the diffuse emissions much better than RACS. These are some pretty pictures for your eyes. Regarding astrometry and flux scale, we see that the difference in the astrometry is sub-arc second, and it is below 1 pixel size of our images. Whereas flux scale is quite nicely matched with RACS. The median varies between somewhat around 10% at the smallest region. we can do, because MeerKAT has such nice large bandwidth, we can do in-band spectral index of the sources. Here I am showing you two such example. And the spectral and the frequency for RAX low, RAX mid, and NVSS are also shown here. And we can see that everything is looking nice with this particular technique. UHF results, you have already seen this in earlier talk. So these results particularly show what we expect from our data release 1 in the left-hand side. So this is going to be the quality of the UHF band image in the data release 1 compared to the RAX low that we have. Okay, so we are doing some science with this also. So we have a nice overlap with kids in both L band and UHF band surveys. So we have created an Xmatch-like pipeline, which is basically done by Mfundo. So we have identified sources from the kids catalog and their redshift, although they are photometric redshift. And we try to identify interesting sources such as this one, which is a very nice large galaxy. Transients are very interesting in our particular case because so let us consider this circular region. We come back to this particular region multiple times at different time scale, depending upon where you are observing. So like it can repeat around 2 to 8 seconds and then 4 minutes, maybe next to when we are doing the setting observation and when we are doing the next day observation. So particularly slow transients are interesting. So Victoria has been working on to create a pipeline for the transient extraction. So this is a simulation where we show that with this particular kind of observation, what kind of light curve do we expect? The work is in progress. There are different ambitious projects that we plan to take up, and any ideas from the audience is always welcome. So this is my summary. So this particular technique on the fly is very important, primarily because it gives us a chance that we don't ask any other time from the telescope. We can do a commensal continuum survey with the H1 survey in line. With upcoming SKA, the sensitivity will be much more interesting. If all the software implementation are fixed, we expect to get nice and interesting continuum sources and catalogs. So we are preparing for our data release, which should be done this year sometimes. Thank you.
Questions? Yeah.
So are you going to study the star formation rate, density, or build the luminosity function of those catalogs?
Yes. So we have done it for this particular small patch already.
Yeah, but eventually you have the optical catalog available for all those patches, right?
Yes. So here we have the DAISY now.
Okay.
And at least here in the L band, we already have the kids.
I have one. Anyone else? Okay, from there. So you said regarding transients, how quickly you can make a map? You have this pattern, right?
Yeah.
This weird.
So transient.
How quickly you can come back to the one, say, the previous field?
Right. So, sorry. Yeah. So
this weird pattern, right?
Yeah.
So if you're looking for transients,
yes. So let me say I'm looking at the
for the
central
same field again and again, right?
Yes.
So how often you come back?
Yeah. So that's what I'm written here. So let me say I want to cross this. I will sample it. Let me say I can sample it 4 times within this circular region. So within the circle, we will have 2 seconds, 4 seconds, 6 seconds, 8 second images.
So every 2 seconds you're coming back.
Yes. No. So once I have crossed this, I'm again coming back in this field after around 4 minutes. And then again, like you keep on doing this.
Yeah, anyone else? If not, let's thank Suman again.